Polarizability and the bending energy of a shallow donor in a spherical quantum dot quantum well made from HGS contoured by CDS. The presence of the impurity in a low-dimensional semiconductors and the application of the external electric field considerably changed the optical and the electronic properties of a physical system studied. So, in this work, we will present the effect of the electric field on the polarizability and the bending energy for a shallow donor confined to move in a inhomogeneous quantum dot based on HGS contoured by CDS.
Our plan will be presented as follows. Fourthly, we present an introduction in which we define the low-dimensional semiconductors and particularly the quantum dot quantum well. Then, in the general formalism, we present the theoretical approach used in our calculation. Finally, we present our result found. In this last decade, the advances in nanofabrication technology have made it possible to manufacture low-dimensional semiconductor materials such as quantum well wire, and quantum dot. A new type of quantum dot structure called a quantum dot quantum well or inhomogeneous quantum dot has been fabricated and studied. The structure experimentally are composed of two semiconductor materials, one of which with the smaller band gap is embedded between a core and the outer shell of the material with the large band gap. The optical and electronic properties depend strongly on the size of the heterostructure, the position of the impurity, and the external excitation applied, such as electric field, magnetic field, temperature, hydrostatic. The optical and electronic properties depend strongly on the size of the heterostructure, the position of the impurity, and the external excitation applied, such as electric field, magnetic field, temperature, hydrostatic. In this work, we used a variational method to calculate the polarizability and the bending energy of an electron bound to a donor impurity confined to move in a homogeneous quantum dot based on CDS HGS in the strong and moderate regime of confinement. We will examine the electric field, the position of a donor impurity, and the size of the dot effects on the bending energy and the polarizability. The theoretical approach. We consider a hydrogenic impurity located at the position R0 of a quantum dot quantum well made from CDS core HGS well CDS cell subject to the action of an electric field outside. If the confining potential is assumed as a model of an infinite deep well. The figure 1 presents the schematic diagram of quantum dot quantum well structure. R1 and R2 are the inner and the outer radius of the quantum dot quantum well respectively. In the effective mass approximation, the Hamiltonian system is written by the expression 1, where VR is confining potential written by expression 2. R1 and R2 denote the inside and outside radius of the quantum dot quantum well respectively. H0 is the Hamiltonian in the absence of the electric field given by the formula number 3. W is the energy created by the electric field, with F is the dimensionless parameter characterizing the strength of electric field. By the expression number 5, we gave the system Hamiltonian of reduced united. By the expression number 6, we gave the Schrödinger equation expressed in spherical coordinates. In order to determine the ground state bending energy and the polarizability, we have used a variational method approach. So we adopt the wave function given by the formula number 7 and 8, where alpha beta are the variational parameters which takes into account the presence of the electric field. The energy is obtained by the minimization with respect to the variational parameters. The bending energy AB is of the impurity is given by the expression number 9, where ET and E sub represents the ground state of the structure quantum dot quantum well with and without the impurity respectively. The polarizability is calculated from the dipole moment and defined as in expressions 10 and 11, where P is the difference of the average value of air in the presence and absence of the electric field. Our results are given in the system of reduced units. We use the effective Bohr radius and the effective Rydberg as the units of length and energy respectively. In this section, we will discuss the results obtained by applying the direct variational method for calculating the electric polarizability by the formula of dipole moment and bending energy of a hydrogenic impurity in the absence and the presence of an electric field in the quantum dot quantum well. Numerical calculations are applied to a spherical inhomogeneous quantum dot based on CDS, HGS, CDS. The physical parameters characterizing the system are given in the table. The study of our physics system, two cases that arise. Firstly, when R1 tends to 0, we will have the case of a homogeneous quantum dot. Second case, in R1 tends to R2, we will have the case of narrow quantum well. In figure 2, we present the donor bending energy as a function of the donor position in a spherical quantum dot. The inner radius R1 equals 0, and for different radius of the structure R2 equal 1, 2, 4, 6, and 8 Bohr radius. This figure shows that the bending energy is more important in the middle and decreases when the impurity moves toward the extremities of the quantum dot to reach its minimum for the ratio R0 on R2 tend to 1. Thus, we say that for a fixed position of the impurity, the bending energy increases with decreasing the dot radio R2. It's due to the distribution of the electronic wave function. Therefore, the decrease of the geometric dimensions of the quantum dot creates a compression wave function, and the electron is closest to the impurity. It is caused the increased bending energy. Our results are in good agreement with the literature. In figure 3, we present the bending energy as a function of the ratio R1 on R2 for two different regimes of confinement as R2 equal 1 and R2 equal 2 for two values of electric field if equal 0.4 and 0.8. We see that the bending energy depends strongly on the ratio R1 on R2 increasing from 0 to 1 and presents a minimum which can be used in nanofabrication of quantum dot quantum well. When the inner radius R1 increases, the donor bending energy moves from the homogeneous quantum dot situation ratio R1 on R2 tend to 0, where the kinetic energy is dominating, to a small spherical layer ratio R1 on R2 tend to 1, where the Coulomb energy prevails and the donor can be considered as a fixed. We note that when the electric field increases, the bending energy decreases, and we note that the electric field effect becomes more pronounced when the ratio R1 on R2 tends to 1. In figure 4, we plotted the electric polarizability of an impurity associated with an electron according to the radius of the quantum dot for different value of the electric field. In this figure, we note that the polarizability decreases with increasing the intensity of the electric field. Our results show that the polarizability increases as the radius of the dot increases. We remark that the electric field effect is more pronounced for large dots, that we can explain that by for large quantum dot, the electronic confinement is negligible, and therefore the results tend to the case of semiconductor series 3D. The electric polarizability as a function of the impurity position is plotted in figure 5. In this figure, we show that the electric polarizability increases with the donor position until it reaches the middle. The ratio R0 on R2 equal 0.5. When the ratio R0 on R2 is greater than 0.5, the polarizability decreases with increasing the size of the quantum dot. This implies that the confinement effect is more significant than the effect of the electric field, and in the case of weak non-significant inverse position in major position, its effect is more pronounced when the impurity is placed at the middle of the dot, and decreases as the donor moves to the end of the dot. We also note that the electric polarizability decreases as we increase the electric field. We have reported in figure 6 the electric polarizability of the donor impurity according to the ratio R1 on R2 of the quantum dot quantum well for value of outer radius R2 and for an electric field strength F equal 0.2. This figure illustrates the competition between the geometric confinement, the size of the quantum dot quantum well, and containment of the electric field on the polarizability. For large value of the ratio R1 on R2, low spherical layer, the geometric confinement is important and the wave function of the electric is very localized. The electric polarizability of the impurity becomes less important and is relatively insensitive to the outer radius R2 of the quantum dot quantum well. For low value of the ratio R1 on R2, large spherical layer, the effect of electric field predominates. The polarizability is strongly dependent on the size of quantum dot quantum well. We note that the polarizability decreases as the ratio R1 on R2 increases. In conclusion, we have studied the polarizability and the bending energy of an impurity located in homogeneous quantum dot in the presence of an electric field. It's clear that they strongly depend on the geometric confinement, the impurity position, the electric field. The polarizability and the bending energy depend on the inner and the outer radius of the quantum dot. Also, it depends strongly on the donor position. It's found that the Stark effect is more important when the impurity is located at the center of the quantum dot quantum well and becomes less important when the donor moves toward the extremity of the spherical layer. When the electric field increases, the bending energy and polarizability decreases. Its effects are more pronounced when the impurity is placed on the center of the spherical layer and decrease when the donor moves toward extremities of this spherical layer. We have demonstrated the existence of a critical value of ratio R1 on R2, which can be used to distinguish the three-dimensional confinement from the spherical surface confinement, and it may be important for the nanofabrication techniques. Thank you for your attention.